when we're looking for maximums and minimums, we might say, what if I want to find the max of the maxes? The most maximum I can be. And similarly with the minimum, the smallest possible value. Can we find these absolute or extreme maximums and minimums? The answer is sometimes, yes, we can. And not surprisingly, calculus will be involved. Well, let's take a look. So the question is, do we always have a maximum? In other words, an absolute maximum, you can't get any bigger than this, that's achieved. And surprisingly, the answer is no, we don't always have it. And even in very simple cases. So we'll take a very simple function. Suppose you look at the function f of xy, which is x plus y, for the region where x goes from 0 to 1 and y goes from 0 to 1. So in other words, when we're thinking about our input, it's this little tiny 1 by 1 square, but we don't include the edge. We can be anywhere on the inside. And we say, well, what's the largest value that the function attains? In other words, I actually plug it in and it says, this is the largest value that I can get out of this function given this restriction. Well, we might say, look, if we want x plus y to be big, the goal is make x big and make y big. So we should head towards the corner. But the problem is we can't get to the corner because it's not part of our function. It's not in our domain. And no matter how close to the corner we get, once we zoom in, we say, look, I didn't get close enough because really, once I zoomed in, I see, aha, I'm actually pretty far away still. And so I can always get closer. In other words, there's a potential for me to get larger. So this function, I do not attain a maximum value. Well, so now we're like, okay, so not everyone can attain this absolute max. In other words, this largest maximum value. But it turns out that there's this wonderful case. And there's this nice fact. It's right here. If we have a nice function, and nice here just means continuous, and our domain is closed and bounded. See, that's what went wrong here. This is a great function, but not a closed and bounded domain. Then the function attains a global max and a global min. In other words, there has to be some place where we plug it in and our function says, this is the largest we ever get out. And similarly, some place where it says, this is the smallest we ever get out. And so we can talk about our global max or min, also known as absolute max and absolute min. And so we're going to focus on our procedure. Now, I will point out one interesting reason why we might want to do this is if we're interested in understanding, say, the range of a function. The range looks at all your possible outputs. And so knowing the global max and global min tells us something about the range of our function. What are our possible outputs? All right, so how do we do it? Well, we're going to take really good advantage of our fact. We say, look, we know it exists. So, since we know it exists, we just have to find it. And in essence, what we're doing is we're going to say we're going to hone in on some candidates. So, we'll say, where might it be? It might be in the interior. Okay, so what do we do there? Well, for the interior, we look at our function and we say set the gradient equal to 0 or see where it's undefined. In other words, we're looking for critical points. All right, so it might happen on the inside, but it might happen on the boundary. And the sets that we're interested in will have boundary because there has to be an edge. It's not unbounded, right? It's bounded, which means there has to be a boundary to our set. Now, how do you work on the boundary? Well, the answer is you say, look, what we do is if I have a region in the plane. So here's my plane, here's my region, and I'm looking here. My region is a two-dimensional region, but what is the boundary? It's one-dimensional. It's a one-dimensional shape. So what we can do is we can look for a way to reduce the problem. So we might go from a function of two inputs and say, well, on the boundary, I can relate, for example, by parameterization or other means, I can relate the two variables together and knock out a variable. Or another way to think about it is I can reduce it down to a single variable. So we say, all right, find the critical points on the boundary. And now we reduce it to sort of a simpler problem. Oftentimes we've gone from 2 dimensions to 1 dimension. Now, as we're doing this, I think it's really important that you don't forget corners, because those are really easy to overlook. But corners are also going to be critical points, especially when we're at the boundary, because those are sort of our endpoints. And you always include the boundary when you talk about critical points. So that first step is doing what? It's making a list. And it's saying, here are the places where you might have a max or a min. Now, the good thing is an absolute max and min, or global max or min, depending on what phrase you like to use, will also be a local max and local min. And so we say, perfect. Our list has all the places where maxes and mins can occur. So our list also has to have the place where the global max and global min occurs. So what do we need to do? Well, we plug the points in. So in other words, we have our list and we start plugging them into the function one at a time. Plug them all in. And now you look at the outputs. Whatever the largest output is, that's the global max, your absolute max. Whatever the smallest output is, that's your global min. Why? Well, because we go through our thought process. We know that it exists. And that's why this fact is so important. We know it exists, and therefore we say, okay, here's where it could exist, and then we check, and then we say, aha, here's where it is. Now keep in mind, you might have several outputs which are equal, and that's okay. When we talk about having a global max and global min, we're not claiming uniqueness. It's very possible for a function to attain a maximum value at several different locations. Think of the function sine that goes up and down. It oscillates. Well, the maximum value for sine is 1, and it hits it at many, many locations. So it's okay if we do have repeated values. So that's the whole idea. It's beautiful. And indeed, you can think of a song. There's a wonderful song that helps you remember the process. And it goes something like this. We're making a list, checking it twice, gonna find out which points are nice. Global max and min are found. Oh, wait, no, that's it. That's the whole song. It's all about make a list. Where could it be? Check the points on the list and pick out the largest and smallest values. And life is good. Well, the idea is pretty simple. And practice, it takes a little bit of work. And I will tell you, the challenging part about these problems is almost always the boundary, step 2. Because oftentimes you have a lot of boundary to work in. You have to say, ooh, let me break it up into a little bit of pieces and handle each piece separately. And so be patient. You get to like 4 or 5 optimization problems to solve just one. What a fun thing. Okay, well, let's go and do some practice. See you soon.